Hi ladies and gentlemen, welcome to lesson 13. Today what we're going to do is we're going to take our first look at the complete solution to the problem ax equals b, and that's the title here that Strang provides. And what we're going to do today is we're going to look at the ideas and the concepts, kind of understand the different options that we can see when we're solving a linear system of equations. And then next lesson, what we're going to do is get into the mechanics about how we actually write these solutions down. Obviously, we'll talk some mechanics today, but the start to finish mechanics of how we're going to do these solutions, that will come in the next lesson. So we want to start right now just talking about ax equals b and what the solutions look like, and he tells us that we're going to have a particular solution and a null space solution. And I just want to explain a little bit about why that is. Those of you who have taken differential equations, you'll be familiar with this idea. What he's doing is he's telling us that we have a solution x which is equal to the sum of part of the null space solution and a part of the particular solution which actually satisfies ax equals b. And this is easy to see. If we expand this out to be axn plus axp equal to b, we can see that that's true because this part is going to be equal to 0. Any null space vector is going to be mapped by a to 0. And what we're left with then is we're left with something that actually solves the equation. And the particular solution is a solution that is particular. The term particular comes from the fact that it is particular to the right-hand side vector. It's particular to b. So looking a little bit more at the mechanics of how this is going to work, we're of course going to use RREF. And as I said, in the next video, we'll get into all of those nuts and bolts. Right now, just need you to understand some of the important ideas associated. This is solvable, and we're going to look at the fixed variables versus the free variables and a little bit about the particular solution. But our primary point of emphasis today is looking at particular situations, which are the full column rank and the full row rank, and what those things actually mean to us. He begins here, so you're going to want to read through all of this. And all he's done is given us some review of the material that we've been covering, things like the augmented matrix. So he just reintroduces that when we're solving ax equals b. We're going to build an augmented matrix, and then we're going to perform Gaussian elimination. And as we continue through the process of coming up with reduced row echelon form, as we've discussed previously, that's Gauss-Jordan elimination. So he walks through this, and then he talks about the importance of the last row. And this gets to the ideas of having rows that are all 0 values. And we'll discuss more of that again in the next video. But what he's saying is, in order for this to be consistent, we're going to have this last equation, of course, be 0 equals 0. We've talked about this before. And that's the comment that he's making here. So the rest of this is largely about solving for the particular solution. What we see is, we see stuff that is similar to what we talked about last time, where we have the RREF, and that's what this thing here is. That's the RREF. And what we're looking for is, we know how to find null space. What we're looking for is, how do we set this up so that it's equal to a right-hand side? Well, let's back up for a minute. We're solving ax equals b, and we know when we do Gaussian elimination, we're going to end up with ux equals c. This is the notation that Strang uses, where we have an upper triangular matrix. Continuing the process, we do Jordan elimination, and we end up with r0x equals d. That's his notation, so I just want to make sure you're comfortable with that. You'll notice throughout this entire process, as we've discussed multiple times, the x is the x. The solution is the solution regardless. And we can solve at this step using back substitution, or we can continue through with the Jordan process, and we end up in this situation. And we know how to take the r naught x and set it equal to 0 and solve. And this is going to give us the x, what he calls x sub n, or null space solution. So that's going to come from there. So what we're wondering now is, how do we come up with this d? And what he tells you, I'll just give you the quick version of what he says. When we're solving for r naught x equals d, we can certainly do that by setting all of the free variables equal to 0. So if we have free variables, then, and of course free variables are required for us to have a non-trivial null space solution. If we have free variables, we can find the particular solution, xp, by setting all the free variables equal to 0. Right? And there are, of course, an infinite number of particular solutions. We could set the free variables to anything we want, but the easier computation is to do it by setting all the free variables equal to 0. So that's not required. It's just something that makes it a little bit easier for us. And he walks through and has this conversation and then talks about the breakdown of the solution into the two pieces. We have the particular solution here, and then something that we'll focus more on next lesson, he has the null space solutions here. And so the sum of those three things, that's what gives us the complete solution to ax equals 0. A comment about the backslash command. So he talks a little bit about the MATLAB backslash command. And it is our recommendation, right, that you don't use the backslash command. It has a couple of problems. First of all, it's only ever going to give you one solution. Secondly, it can give you incorrect information in the situation where we have matrices that don't have an invertible piece to them, right? So instead of using the backslash command, use RREF. The RREF gives us access to the complete solution, the null space part of the solution, and it's very easy to find particular solution by taking the free variables and setting them equal to 0. So we are going to use RREF, and that is the point of the next video. We're going to walk through the steps of exactly how that gets done. So the conversation here, starting at the top of page 106, is about consistent versus inconsistent systems. We're leaving you to read this. We've already talked about consistency versus inconsistency, and that's all available for you to read. The two things that we really want to focus on for today are the sections where he talks about full column rank. And what I'm going to do is isolate to the rectangular situation only. So we already discussed the square systems back in chapter 2. And we will definitely tie those back in, but the primary focus here is where we are talking about rectangular systems. So what he's talking about in this conversation is situations where we have more rows than columns. Always we recommend that you write this down. So more rows than columns is something that looks like this. So that's my coefficient matrix A. And then I have x is equal to, and I have some vector b that looks like this. Now, the situation that he is specifically honing in on here is A is full rank. And by full rank, we mean it has its maximum possible rank, which is n. Remember, the maximum rank for any rectangular matrix is the minimum of the number of rows or columns. The rank can never be larger than the minimum of the number of rows or columns. So in this case, we have the rank of A is equal to n. What does that mean for the RREF? When we do the RREF of the augmented matrix A with B, we are going to end up with what kind of a matrix? And he talked about this a little bit in the previous section. It might be worth going back to take a look at it. We're going to end up with the identity matrix over some 0, depending on how many 0 rows we have, because we know we have redundant rows. We know we have equations that are redundant. So we're going to end up with this thing, and then of course we're going to have the d vector in here as well, and that d vector will be the full stretch, like this. And so what we can see is we can see all from this picture, which is why we recommend the pictures. From this picture, we can see all of the information. So don't be confused. These aren't ones. This is just saying that the vector D stretches from for all the rows, right? It's not like the vector D is shorter. It's full. It's augmented into the system. So let's take a look at what he says. He says all the columns of A are pivot columns. There are no free variables. And we can see that right here. We have the identity matrix as the first n rows, right? So this break here is occurring, and we have an n by n identity matrix. There are no free variables. The columns of A are linearly independent. So what that means is then the null space is trivial. We only have x equals 0. So when we go to build our solution, x is equal to the null space plus a particular solution, there is no null space vector because we have no null space. Then finally, what he talks about is we have a unique solution if we have a solution. And the point about if we have a solution is easy to see from the picture. Notice what we have down here. We have the bottom part of D, and we have zeros. So the system is consistent only if all of these values down here are actually 0 values. So that all of those equations are 0 equals 0, 0 equals 0, 0 equals 0. If not, the system is inconsistent. So this is the general flow of what happens when we have more rows than columns and we have full rank. Definitely you want to take a look and read through his example here. By contrast, we're going to take a look at the situation where we have full row rank. So full row rank is where we have more columns than rows and the rank is full. Again, recommend a picture. So what we're talking about in this situation is we're talking about an A matrix that looks like this, and we have X, and that's equal to some B vector here, which would be a short vector like this, which then means that my picture back here is a bit misleading had I drawn a full vector, right? X, remember, only has as many components as I have columns. That's why I have a long X here. So this picture is useful to be able to figure out what's going on. Again, we have full rank. The rank in this case is equal to M. So let's take a look, just like we did back up here. What is the RREF of A augmented with B? So we're going to RREF, and we're going to build our augmented matrix as we always do, A augmented with B. That's going to be equal to, and now what we're going to end up with is, we're going to end up with this identity matrix, and we're going to end up with what Strang calls F. Right? So I'm not going to include that in there, but we're going to end up with extra information in here to fill out all of the columns. And then we'll have the last column, so let me erase. After everything from A, we'll end up with the D vector. And of course, as always, the D vector is full size there. So just looking at the picture, what do we know? What do we know about X equals the null space plus some particular solution? Well, first of all, we know the system has to be consistent. We have all of the linearly independent vectors in the columns of A that are required to build any B vector. So we know the system's consistent. Moreover, we have free variables. Every one of these extra columns beyond the identity, that is associated with the free variable. We know that that's the way it's going to work out. This is what Strang calls the F matrix over here, which we've kind of ignored because this situation is a special case. And then, of course, we have our D vector. So he provides some information about this, and let's just take a look at what he says down here about this particular situation. All the rows have pivots, so we don't have any zero rows. And we can see that. Let me copy and paste to bring this down so we can see it more easily. All right, sorry about that, yeah. So here it's a little easier to see. So we can see every row has a pivot. So there are no zero rows. In the previous situation, we had the possibility for all zero rows or an inconsistent system. Then he continues on. Let's take a look. Ax equals b has a solution for every right-hand side vector. We already talked about that. Because the identity matrix is in here, and let me give it the right size. This is IM. That matrix means that the first m columns of A are a basis for the space Rm. Right? So Rm is the column space of A, and we have full coverage for Rm. And we have a solution because every B is going to be inside of Rm. So it has to be inside the column space, so we know we have a solution. That's what he says. That's that comment right there. And then finally, in the situation where we have more rows than columns, or sorry, more columns than rows, we are guaranteed to have what we call an underdetermined system, or we're going to have free variables. So we're going to guaranteed to have free variables, and those free variables are associated with the null space. So we know that we're going to have a non-trivial null space, and we also know we're going to have a solution. So this is a situation where we know we have infinitely many solutions, period. We know that's the case. It's worth looking through. You don't want to memorize this. You want to be able to draw the pictures and understand. Right? Memorizing these types of things, that's not where we want to be. Again, the commentary about the F's are here. Let me just highlight the two examples that we looked at. This is the situation where we have full column rank and we have more rows than columns. And then this situation here is the situation where we have full row rank and we have more columns than rows. So these are the two cases that we talked about, first and second, respectively. So it's worthwhile to look at that. We have not, and we really are not going to have this conversation. It's worth noting that both of these situations are satisfied when we're talking about a square system. If I have a square full rank system, what do I know? So we have AX equals B. Now we're back to chapter 2. A is square, n by n, and the rank of A is equal to n. Well, now I know a whole lot. As we talked about, the following are equivalent. I know that AX equals B has a solution. I know that solution is unique because I know the null space of A is only the zero vector. It's the trivial null space. I know the column space of A is the entirety of Rn. We know A is invertible. We know the columns are linearly independent. We know all of these things about A. That's the special case where we have a square matrix. The other piece of this that I want to just touch upon is the conversation he has down here about using random variables, or random numbers really, to try to solve the system. So we use the RREF. It's actually computationally expensive when we're trying to solve systems. There are some techniques that are faster when we find special cases, things like tridiagonal matrices or pentadiagonal matrices. There are much faster techniques, but still the systems in general can grow enormously large. 10 to the 9th, 10 to the 10th, 10 to the 12th, we can have these enormous systems that no computer on the planet, supercomputer or otherwise, can actually solve. And so his comment here is, hey, there are techniques where we can come close to finding a solution using random numbers and guessing. This is based upon an idea similar to Monte Carlo. Monte Carlo is where we are guessing and then checking to see how well our guesses work. We'll talk a little bit about that in this class because it's such an important idea and it's quite important to the OR and data science majors, but it's not a objective of the course, so we won't go into it in depth. Last thing I want to talk about is the first worked example here. So Strang goes through a full example of how he would do this, and what he does is provide us with the steps in which he would do things. So he starts out here, step one, he's going to build an augmented matrix, and then he's going to apply Gaussian elimination in order to come up with an upper triangular system. That's what he says. Okay. Then he's going to find conditions for which he has a solution. Okay, that's fine. In the case where that needs to be done, he could do it at this point in time. Then find the column space. The column space is determined by the pivot columns. And the pivot columns that are inside of the upper triangular matrix are the same pivot columns as in R. So let's be clear about that. When we're at ux equals c, here we have pivot columns. And when we go to R0 x equals d, those pivot columns are the same. R0 and u have the same pivot columns because the columns of A are linearly independent, regardless at which point we stop to take a look at them. Then he talks about the null space and finding the null space of A and what are the special solutions, because that's going to be part of our solution to the system. Remember, as we talked about today, we are solving X is going to have a null space component, and it's going to have a particular solution satisfying the given right-hand side vector, the given B. So then he goes on, and his fifth step here is reduced row echelon form and finding the reduced row echelon form. All of this is fine. I recommend, and what we will do in this class is, step one is going to be RREF. So the first thing we are going to do is RREF. And that is going to provide us with the information about, is the system consistent or inconsistent? What is the column space? What are the free variables? How do I build the special solutions for the null space? What are the fixed variables or the pivot variables? All of those things are given to us from the RREF. And we will work through some examples. That's really what the next video is all about. So let's take a look at our questions for today. So these are the questions. You'll notice these questions are more theoretical in nature, right? Not so much about solving AX equals B. This is really more about understanding the situations that we were talking about with respect to the rank and the number of columns and the number of rows that are in the matrix. Emphasis, of course, on the column space and the null space. All of this is tying what we just talked about associated with the systems and the specific situations we might find ourselves in with previous material. We will want to make those connections spiraling back to tie everything together. So take a look at those, be ready for class, and then we will talk about how to actually come up with the solutions during the next lesson. Thanks.